So good evening all. So in your last class in mass spectrometry, we discussed some selective fragmentation pathways for a given organic molecule starting from alkanes, alkenes and alkynes. It is same way we discuss some selective rules regarding to the mass spectral fragmentation starting from McLafferty, one more is double McLafferty, indirect McLafferty, one more is oxygenamine we discussed. Okay, so almost all 14 rules we discussed. Now take 15th one. So after that we will see some more selective applications on mass spectrometry. Okay, now this is your 15th mass spectral rule. So this is only for carbonyl compounds. If I take any carbonyl compounds undergoes 2-alpha heterolysis, 2-alpha heterolysis and 2-alpha homolysis. Two possibilities are expected here. So 2-alpha heterolysis, 2-alpha homolysis are characteristic fragmentations for carbonyl compounds. Carbonyl compounds undergoes 2-alpha heterolysis, 2-alpha homolysis. If I take any carbonyl compound, these two possibilities are expected. So these 2 points you need to remember. Take any carbonyl compound, two possibilities are expected: alpha heterolysis, alpha homolysis. Okay, so this is one of the example. See, carbonyl compound after formation of molecular ion. How to write molecular ion? By removing one of the electron, you can write like this: radical, cation and here lone pair. Okay, so here I want to do alpha homolysis. Alpha homolysis. If I do alpha homolysis, can I break this side or not? This is called alpha bond. So break this side. This radical forms double bond. So if they form double bond, you will get like this, and here there is a formation of a methyl radical. So this is called alpha homolysis. See here, right side methyl, left side methyl is there. You can break any one of this bond and finally you will get acyl cation. Right? This radical forms a bond. Now you will get acyl. Okay? Suppose if this particular part having a two different groups here, molecular ion formation takes place and forms a radical cation like this. Same alpha homolysis I am saying. Right side, left side both are possible. So right side ethyl is there, left side is methyl. So whichever fragment have a tendency to give a stable radical, that side we need to break. So I can break towards right side. If I break right side, this radical forms C, CH3 triple bond O plus, and what is removed here? This is CH3 CH2 radical. Is it right? Ethyl radical is removed. Suppose if I want to make a heterolysis, C double bond O CH3. This is radical cation and I want to make alpha heterolysis. Alpha heterolysis. Heterolysis means like this. See, here 2 electrons, here also 2 electrons are there. I want to add this electron here. If I add this electron over here, then this is removed in terms of, okay, how it is removed here? Cation or not? This is removed in terms of cation. Then how CH3 is going to be removed here? See, this radical is as it is or not? This electron will be added here. So if you add electron, you will get a lone pair and here one more lone pair, and this CH3 is removed in terms of what? CH3 plus. That is a way of fragmentation. This is alpha heterolysis, this is alpha homolysis. Both are possible for carbonyl compound. So when carbonyl compound is available anywhere else, anywhere if carbonyl compound is present, try to break these bonds. This bond if you break, you will get a clear answer. Okay, suppose if two different organic parts are available, C double bond O, CH2 CH3, here radical cation and this is lone pair. So here I am using alpha heterolysis. Can you guess which side should I break? Ethyl side or not? Is it ethyl side? It is ethyl. So now here bond pair of electron, it will be added. This electron will be added here. So after addition of electron, what is your answer? Already one lone pair. Here I am adding one extra electron, and see this radical as it is, and what is removed? CH3 CH2 plus. What is MZ value of this one? MZ value is 29. 12 plus 12, 24. 24 plus 5, 29. And what about this acyl? Acyl implicit value. 1, 2, 3. 36 plus 4, 43. Implicit value 43 or not? This you remember. Say I am not writing implicit value for this fragment. Why? It is a radical. So only one point you need to remember for any carbonyl compound. Carbonyl compound cleaving alpha bond is a most important one. Out of these two, alpha homolysis is preferred over heterolysis. So in your examination, if they given heterolysis and homolysis, both are possible. But intense peak belongs to which one? Alpha homolysis. Suppose if I take a carbonyl compound having a benzene. This is benzene. Here C double bond O, radical cation, and this is CH3. Now alpha homolysis is predominated as compared to heterolysis. Now which side should I break here? See, can I break bond between this side or not? See, this bond is weaker as compared to this one because benzene conjugate to carbonyl. When benzene is conjugate to carbonyl, there is a delocalization of pi electron takes place. So on that time, it is the strongest bond, it is the weakest bond. Must prefer always a weakest bond to dissociate. So I would like to break this bond only. If I break this bond, this radical forms a triple bond. This radical I am saying. So on that time, you will get double bond and here carbon, oxygen, triple bond plus. And what about next? This is CH3 radical. Right? This radical forms triple bond. Plus will be as usual. CH3 is removed in terms of radical. And what about implicit value for this fragment? This is already given. Implicit value. Just count and say the answer. And write down. Very easy. 100? Yeah, 105, not 102, 105. Total how many? 6, 7, 8 will be there. 8 into 2, 8 into 12. 96 or not? 96 plus 400 and this is 5. 1, 2, 3, 4, 5. 5 hydrogens are there. So this is the most important characteristic fragmentation of carbonyl compound. If anywhere carbonyl compound is given, it is the characteristic fragmentation. Clear? These rules you need to remember. Everywhere it will follows. While explaining functional group, you need to give the answer for this. Okay. Next, 16th one. This is last rule. So it is mixture of variable fragmentations are observed. So this is called fragmentation elimination. So I am eliminating a atom or group, that is called fragmentation elimination. So best example, dehydrohalogenation. What is the meaning of dehydrohalogenation? Loss of HX. Fragmentation elimination. Right now see, multi-center fragmentations we are learning with respect to functional group. Some functional groups have a tendency to lose at a time some selective groups. So during that particular elimination of groups, we are not breaking one bond, we are breaking multiple bonds. So if you are breaking a multiple bond, that is called multi-center fragmentation. So that's why that group will be eliminated. That is called fragmentation elimination. So especially dehydrohalogenation means, just listen, this is RCH2 and here one more CH2 and this is X. Is it a alkyl halides or not? 70 electron volts or electronic impact. Remember, there is a formation of radical cation. Okay, and this hydrogen will be as usual. Can I write like this? This hydrogen. Now the question is, I want to remove halogen from this carbon, hydrogen from this carbon. If I remove hydrogen halogen in the form of HX, that is called dehydrohalogenation. Right? So what is this bond indicates? Is it alpha or beta? Alpha. And what is this? It is alpha or beta? Beta. Okay. Now I am breaking this bond heterolytically. Here what is the charge you will expect? Positive. So if this electron, if you add here, then this positive charge will be disappears or not? And what about here? Radical will be as usual or not? So I would like to remove this carbon halogen bond in the form of radical. And here what is the charge I created? Positive. And here I am cleaving homolytically. So here one radical is left. Now halogen is removed in terms of X radical or not? Halogen is removed in terms of radical. But what about this carbon? CH2 and C. Here positive and what is this? Radical. Can I write radical cation? So heterolytically I cleaved here. I written CH2 plus and here CH dot. So these two I would like to write like this. Can I write like this? Radical cation. Can I? Then what is removed here? I removed HX in the form of neutral or not? So within this molecule what I removed? HX is removed. So loss of HX is nothing but dehydrohalogenation. So on this carbon halogen is removed and this carbon hydrogen is removed. Is these two carbons are adjacent to each other or not? Yes, these two are adjacent to each other. So that's why it is called 1,2 elimination. 1,2 elimination. So my question is whether this fragmentation is possible or not according to the rule. According to mass spectral pathways, is it a odd electron ion? Odd electron ion. Odd electron ion undergo fragmentation will give odd electron ion and what is one more? That is neutral. Otherwise you can say this is a radical cation. It is responsible to give radical cation and what is this? That is neutral. Okay, otherwise you can say even electron ion. Odd electron ion means it is an even electron and this is neutral like this. Anyway you can write. Means whatever fragmentation we are doing, that fragmentation never takes place randomly. Always fragmentation follows one particular order. That order is mass spectral order. We are following odd electron rule. One more is even electron rule. According to odd electron rule, if they undergo fragmentation give odd and even. If it is an even electron species, if they undergo fragmentation give even and even. So don't think that odd will give odd odd, even will give even even. That is wrong. So this is called dehydrohalogenation. Okay, is it dehydrohalogenation possible? Now see, can you say is it alpha hydrolysis? Is it alpha hydrolysis or not? Yes. Then what is this? Is it beta? Is this bond is beta? So carbon, hydrogen, and here C, don't write. This is hydrogen and here hydrogen, and here I am written halogen or not. Halogen is a functional group. So this is molecular ion. And what about this bond? This bond is alpha bond. What about this bond? This is beta. This is beta. This is beta. This is beta bond. 3 beta bonds. Then what about this bond? This is gamma bond, not beta. Okay? Halogen attached first carbon bond is belongs to alpha bond. Next bonds are belongs to beta. So now this is alpha heterolysis, gamma homolysis. Now my question is whether they take simultaneously or step by step. Simultaneously. At a time they will take. They never take back to back. It is not a successive fragmentation. What is the meaning of successive? Successive nothing but step by step. First this one, next this one. That is not takes place in multi-center. Multi-center nothing but at a time multiple centers undergo fragmentation. At a time we are removing these two. We are not removing this first, later we are not removing like this. Okay, we are removing halogen in the form of radical, hydrogen in the form of radical. So if this halogen want to remove in the form of radical, it should be heterolysis. It should be homolysis. Clear? Now see this. So one more I am giving. This is CH2 and here radical cation, and here I am writing CH2 and here hydrogen. So I want to remove halogen in the form of radical and here hydrogen in the form of radical. Then what will expect? This is CH2 taken how many times? N times. And this is CH2, and what is this? Is it CH2 or not? Halogen removed in terms of radical. So here what is the charge? Positive. Here radical. So can I put one bond? And I am writing a radical cation. So whenever if they written like this, don't think that there is no bond between these two carbon. Bond is there. But here positive charge, and what is this? This is positive charge and here radical. So in order to write clearly, we are writing a bond between them and we are writing this radical cation outside. And what is removed out? HX is removed out. Okay? Suppose if n is equal to 1, what do you expect? If your n is equal to 1. 3 membered or not? If n is equal to 1, 1, 2, 3. 3 membered. So that is called 1, 3 elimination. Suppose if n is equal to 2. Here if I write 2. 1, 2, 4. So now what is the kind of elimination? 1, 4 elimination. N is equal to 3. 1, 5 elimination. N is equal to 4. Then 1, 6 elimination. Like this, it is keep on progress. Means every time which member rings we are getting? 1, 3 elimination means how many member ring? 3 membered. 1, 4 elimination means 4 membered. 1, 5 elimination, 5 membered. Then 1, 6, that is 6 membered. Means whenever if you are removing halogen from haloalkanes, there is a possibility of forming a ring. That is called cyclization. There is a cyclization possibilities takes place. What is the meaning of cyclization? Formation of a ring. Whether I am preparing any ring or not. Yes, I am preparing a ring. Okay. So during dehydrohalogenation in a long chain halogen derivative. Okay. During dehydrohalogenation in a long chain halogen derivative, there is a possibility of preparing variable types of rings. That is called cyclization. So indirectly what I am saying is halogens undergo. Is it halogen derivative or not? Halogen derivative nothing but haloalkane. Haloalkanes undergo dehydrohalogenation, also called cyclization in a long chain. Is it a 1, 2 or not? Now is it a 1, 2? No, it is 1, 3. 1, 2, can you prepare a ring between two carbons? No. 1, 3, 1, 2, 3. You can prepare a ring. 1, 2, 3, 4. You can prepare a ring. So 5 membered, 6 membered, 7 membered. So this is possible only for large membered rings. So suppose, just listen one more. If it is only 3 carbons are present, if I write CH2, 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 if I remove this hydrogen in the form of a radical, then I can put a double bond between this and this. Then you will get a halonium. Right? After getting halonium, is there any gamma carbon? Is there any gamma carbon in this one if n is equal to 1? No. Suppose if I take n is equal to 2, gamma carbon is there or not? On that time, indirect McLafferty possible. What is indirect McLafferty? Indirect McLafferty, initially molecule not having any unsaturation, but after homolysis at one particular place you will get unsaturation. That unsaturated part, with the help of gamma carbon, hydrogen, there is a McLafferty rearrangement is possible. That is called indirect McLafferty. Clear? Direct McLafferty means there is a requirement of unsaturation. Indirect McLafferty means during progress of fragmentation you will get an unsaturation. That unsaturation responsible for McLafferty. Clear? So whenever I say halogen compounds in your mind, when halogen derivatives, halogen compounds are given, think about alpha hydrolysis, beta homolysis, multi-center fragmentation to give elimination reactions, to give variable rings. And one more, this is also an example of cyclation reaction. Dehydrohalogenation is an example of which one? Cyclation if carbon chain length is increases. Clear? So suppose if I say the haloalkanes, what type of fragmentations you can expect for haloalkanes? Haloalkanes undergo which type of fragmentation? Alpha hydrolysis. See, if I remove this halogen directly like this, after getting radical cation, if I this, then what is the charge you will expect? Positive. Possible? Then, one more molecule, I can remove hydrogen, halogen or not? Yes. Other molecule I can remove this hydrogen and this radical and halogen forms a double bond. After that you will get indirect McLafferty. Suppose if I remove hydrogen, halogen from third carbon, cyclation. This all are belongs to characteristic fragmentations or possible fragmentations of one functional group. Suppose if I say haloalkane, can you give some fragmentations of haloalkane? I am saying. What are the fragmentations you can expect for haloalkane? Haloalkane means halogen attaches to alkane. What are the possible fragmentations? What are the possible fragmentations? First one, alpha hydrolysis. Next, beta homolysis. After beta homolysis, you will get a double bond between them. So when you get a double bond, then what will you get? Indirect McLafferty. And halogen derivatives also give cyclation. So means whenever if I give one functional group, you are in a position to remember some selective fragmentations according to the rules. Clear? Right. So here you write elimination 1, 3 elimination, 1, 4 elimination, etc. So second type of reaction for fragmentation elimination, dehydration. Dehydration nothing but loss of water. Is it dehydration is elimination? Right or not? See, drinking water is a addition reaction. We are adding water in our body. So whenever if you run, what happens? Sweat will come out. Automatically water levels are decreases in our body. So that is called elimination. So addition, elimination is a common process in our body. Okay. So elimination is also a fragmentation reaction. So here I am going to take one alcoholic group. See, this is OH. Here radical cation I am writing, and here hydrogen. Now multi-center fragmentation. I can remove this one and I can remove this one, similar to halogen. Then what will get here? Radical. So this is radical, and what about this carbon? This carbon carry positive. So can I write double bond? And what about this radical cation? And what is removed? Water. Loss of water is called dehydration. Clear? Suppose if I take a molecule cyclohexanol, you remember this molecule. I will ask these questions. Cyclohexanol, it is readily showing a chair form like this. Chair form. With respect to this hydroxy, which hydrogen is very closer? 1, 2, 3. Third carbon hydrogen is very closer in chair form. Now this is called axial hydrogen. Now this radical cation formation takes place here. Now here I can remove hydroxy in the form of radical and this hydrogen in the form of radical. So here what will you expect? This is radical, and what will you expect here? Positive charge. So I can remove water molecule or not? So if I remove water molecule, can I put single bond? This is radical cation, and what is removed here? Water. Can I? Suppose I don't want to write a single bond here. What should I do? I don't want to write a single bond here. Can I write radical? Then here positive charge. So hydroxy, hydrogen both are removed from adjacent to each other. So I can say it is 1, 2 elimination. This is 1, 2 elimination. Then what about here? 1, 3 elimination. 1, 3 elimination. Okay. So same molecule I am going to repeat in one more way. Hydroxy group I am writing a chair form. Now it is a boat form. This is hydroxy and here hydrogen. Now which hydrogen and hydroxy very close to each other? 1, 4 is closer. In this 1, 2 is closer to remove water molecule. Here 1, 3 closer. Now here 1, 4 is closer. So here what I am saying is, after formation of molecular ion, remove water hydroxy, remove hydrogen. Then what happens? This boat form will be getting a new sigma bond, and here a radical cation, and what is removed out? This is H2O. So here this is an example of 1, 2 elimination. Now what do you observe among these four? In dehydrohalogenation, hydrogen, halogen is removed. But here hydroxy, hydrogen is removed. The concept is, should I remove hydroxy from this carbon always or not? Yes. Wherever hydroxy is there, that hydroxy is a target for mass spectrometric instrumentation to remove that hydroxy in the form of radical. Then if you are removing hydroxy from here, then definitely we need to remove hydrogen from here. Okay? But not always. That depends upon the skeleton. See, here I removed from 1, 2. But here I removed from 1, 3. Then here I removed from 1, 4. On which basis I am removing? Why not 1, 2 here? Why not 1, 2 here? Why not 1, 3 here? This kind of questions you will get or not? So, dehydration possible based on the orientation of hydroxy and hydrogen, whichever is closer. Here this hydroxy, hydrogen very closer to each other. That's why they are undergo dehydration. So dehydration depends on which one? It is depends upon the skeleton structure. It is not depends every time alpha position, beta position, never takes place dehydration. Right or not? Don't think that from two adjacent carbon dehydration is possible. Maybe from higher dehydration is also possible. Now one more important point is similar to this. See, same question I am giving now. Here I am giving a radical cation. Alcohol, long chain alcohol I am using. This is radical cation and here lone pair. Now I want to do heterolysis here and here homolysis here. What is removed? CH2 taken n times and this is CH2 and this is CH2, and is it radical cation or not? What is removed here? So concept is same or not? In place of halogen, if I take hydroxy, I can prepare a rings here, 4 membered, 3 membered, every time I can prepare. See, this is almost all equal to halogen only. Halogen undergo dehydrohalogenation, alcohol undergo dehydration. Okay, alpha hydrolysis, beta homolysis, oxonium undergo onium ion fragmentation, oxonium also undergo indirect McLafferty. See, same thing we are learning. Suppose if I give alcohol, alcohol undergo which type of fragmentation means what you will give? So give the fragmentation modes of alcohol. What type of fragmentations are expected for alcohol? Alpha hydrolysis, then beta homolysis. See, if I remove this hydrogen in the form of radical, this carbon, this oxygen forms a double bond or not? Say yes or no? If I remove this hydrogen in the form of radical, I am saying. Now you will get oxonium. Oxonium having a gamma carbon hydrogen undergo indirect McLafferty. Oxonium having beta hydrogen followed by alpha homolysis. It is also undergo onium ion fragmentation. Indirect McLafferty possible, onium ion fragmentation also possible for this one, and they also undergo dehydration. So dehydration is a single step or multi-step? Single step or multi-step? Single step. Don't think that, sir, first I want to remove hydroxy, next I want to remove hydrogen. It is not takes place like that. At a time remove hydrogen and hydroxy. Single step elimination reaction. Clear? Based on mass spectrometry, we can guess very easily which atom is removed from which position. Based on this spectra, we can determine which atom is very closer to constraint group. See, this is most favorable for this hydroxy to remove. I am not removing second position, third position hydrogens, because dehydration possible with respect to hydroxy and hydrogen which are very closer to each other. Clear? Right. That is dehydration. Clear? So that is dehydration. Second elimination, fragmentation. Third one, decarbonylation. Not decarboxylation, decarbonylation means loss of carbon monoxide. Decarboxylation means loss of CO2. Decarbonylation means loss of CO. You remember this point. So decarbonylation is elimination reaction or not? Yes, I am removing carbon and oxygen. So in this case, what happens, see, this is a 7-membered ring, putting carbonyl group over here. Now I am writing a radical cation over here now after electronic impact, right? Now what I am doing is, here I am doing heterolysis. Now here I am doing homolysis. See the difference in arrows. This is homolysis and what is this? Heterolysis. So this radical as it is, towards this side. But what you will get here? Radical. But what about this side? Here you will get positive or not? Now this electron I am adding here. This electron I am adding here. So if I add this electron, you will get double bond, and what is the charge? Positive, and what is this? Radical. And what about this carbon oxygen? Carbon oxygen removed in terms of neutral or not? This carbon carry 2 electron. If this electron added here, it becomes neutral. Right or not? So initially you will get carbon oxygen double bond. Here lone pair, here 2 electrons are present. There is a coordinate covalent bond takes place towards back side. Coordinate covalent bond towards this side, and finally this becomes a neutral. Clear? So on this case, what happens, see, there is a presence of empty orbital, carbon. Carbon becomes a carbon in this case. Now this non-bonding electron, once they share and forms a coordinate covalent bond. So later on this coordinate covalent bond becomes a covalent bond clearly. On the time this carry negative, this carry positive. So this is carbon monoxide structure. Clear? Otherwise simply if you are confusing over here, you better write CO directly. Clear? So what you observe is C. I am showing one more time. If you break here, these 2 carbons electrons are as it is. And what about this electron? This electron added here, and it become like this. Carbon oxygen. This is extra electron coming from carbon, and this lone pair as it is. And here how many electrons you are getting now? 2 electrons. First you write down like this. Clear? So after that what happens is, this I am writing in the form of a ring. Can I put a bond over here? If I put a bond here, double bond, and here double bond, and I am writing one more double bond. This is double bond, and here one more double bond. Can I write radical cation? What is MZ value of this one? This and this both are same or not? Both are same or not? This one. What is MZ value of this fragment? How much? 78. MZ value is 78. Now what I am doing is, this molecule, can I take this as reference? Now here one hydrogen is there or not? Here how many hydrogens are present on this carbon? One hydrogen or 2 hydrogens? One hydrogen only. Here one hydrogen, still one hydrogen. Now I am breaking this one. If I break here, what you will get? If I break here, what you will get? Radical. This radical combine together and forms a new bond. This is a real bond. And what is the charge here? Positive charge. So what about MZ value of this one? This is 77. Once if you get 77, what is the common fragment? 51. 77, 51. Yesterday I explained. Whenever if you are getting 77, definitely you will get one 51 peak. Clear? It is a radical cation, but this is only cation. So there is a loss of hydrogen in the form of radical. It is a odd electron, radical and cation. Following rule or not? Yes. That is decarbonylation. So this you can also write like this. See, this fragment, here oxygen and C, carbon having a D2 bond, coordinate covalent bond. Okay. So means this lone pair donated to empty orbital of carbene. Then this lone pair will be as usual. This lone pair is donating over here. So finally this you can also write like this. Carbon monoxide, carbon bearing negative charge. What about oxygen? Positive charge. Like that also you can write. So what is this reaction? Decarbonylation, not decarboxylation. In fast generally you people say decarboxylation, not decarboxylation. Decarboxylation means loss of CO2. Clear? This is most important for your exam. So directly some basic questions they are asking. Identify the order of decarboxylation. Identify the order of decarbonylation. Dehydrohalogenation order they are asking. So first of all you should know how to remove the fragment. Later on it is very easy. So whenever if you are removing CO, try to remember these structures. It can also helpful for boron mechanism. Organometallic compounds, boranes will be there. In boranes, we are converting a organic compound into alcohol by using this method only. Trialkyl borane reacts with carbon monoxide in presence of peroxide basic medium. We are converting into alcohol. So this is one of the technique to remember. Clear? Now take one example as phenol. Phenol also undergo decarbonylation. This point you remember, double bond, and this is phenol. Now phenol molecular and I am writing. This is undergo tautomerism. This hydrogen migrate here, transfer here. So tautomerism responsible to give double bond O. Here radical cation lone pair, right? This is undergo tautomerism will give carbonyl. Now this is remove heterolysis, homolysis. What is your answer? Heterolysis, homolysis. Here double bond and here double bond, and what is the charge here? Can I write radical or charge? Radical. Here positive. So this is removed in terms of CO. I don't want to write CO structure regularly. You remember that. Now can I put a bond between them? See, here I removed CO. CO is removed. Now this fragment can I write like this or not? This is double bond, and here I am writing radical cation. What is embedded value of this one? Fast. 65 or 66? Hmm? On this carbon, how many hydrogens are there? 2. Here, 1, 1, 1, 1. Here also same. I not removed any hydrogen. I removed only carbon, oxygen only. So, you need to count like this. 1, 2, 3, 4, 5. 5 into 12, 60. 62, 63, 64, 65, 66. One hydrogen is sufficient to do mistake. Implicit value is how much? 66. Now I want to remove one hydrogen. See, here if I remove one hydrogen from here, this radical forms how many membered ring? 5 membered or not? Can I put double bond here? Double bond, double bond. This radical bond, and what is the charge here? Positive. So what about implicit value? Now this is 65. Clear? That is a way of fragmentation. So if you know mass spectral fragmentation clearly, you will enjoy mechanisms. Otherwise, impossible to remove the negative thought on mechanism. Generally, people think that you need to behead the mechanisms. That is wrong. Don't behead mechanisms. Try to understand the mechanism. Try to understand the key point in mechanism. If you understand the key point, automatically you can write the answers clearly. Clear? So you work out this and say the answer. Double bond, and here 5 membered ring, and this is C double bond O radical cation. So go for decarbonylation. What is the answer? 4 membered or not? So remove heterolytically, remove homolytically. So this benzene is as usual 4 membered. Now this will be as usual. This is radical cation, right? Here this carry positive. Here carry. Suppose if I remove one hydrogen, possible? Hydrogen is there. This carbon, any hydrogen is there? No. This carbon, any hydrogen is there? No. So it is impossible to write cation. Radical cation only. Like that. So loss of CO, here heterolytic and this is homolytic. What is the answer? Can I write a 3-membered ring or not? This is 3-membered ring, and here see, this is radical cation. Right? So what is the charge here? Positive. What is the charge here? No charge. You will get radical. So means here positive, here radical. Now I want to remove CO homolytically. Both sides homolytic fission. If I remove one more CO, then what is your answer? Now, can I put a double bond between them or not? Then can I remove CO? Then can I write radical cation or cation? Still radical cation. See, here what I am doing now, is it 2 homolysis or heterolysis? This is C double bond O, this is homolysis, it is also homolysis. Here what is the charge actually? Positive. Here radical as it is. So if you break this bond, here you will get one radical, here one more radical. That radical will give double bond. Now my question is whether it is possible or not. How to confirm? Question is whether this fragmentation exists or not. How can we confirm? By using pathways. Mass spectral pathways. See, it is a radical cation or not? Now what is this? Radical cation and neutral. Possible? If any radical cation is there, that may give radical cation and neutral. Possible. Yes, this is correct. Like that we can check whether fragmentation is right or not. Follow the rule. That's why only 2 rules are sufficient. Even electron rule, one more is odd electron rule. If you know these 2 rules, concept is over. You know what is the selective direction for the fragmentation. Okay, so for that we need to learn starting of mass spectrometry clearly. Right. Clear? So this is ortho elimination. Next fragmentation elimination is ortho elimination in aromatic compounds. So dehydrohalogenation, dehydration, decarbonylation, mass spectral fragmentation of carbonyl is over. Next is ortho elimination. So generally you know what is ortho? If any benzene is there, if any 2 substances are adjacent to each other, that is called ortho. Okay. So mostly this elimination applicable for aromatic skeletons. Means benzene and their derivatives. Okay. So you write one statement. See, aromatic molecules having proper ortho substitutions undergoes 1,4 elimination. This 1,4 elimination also called ortho elimination. Okay, so due to closer proximity, means they are very close to each other, that's why this ortho elimination is possible. is known as ortho elimination. Aromatic molecules having proper ortho substitution undergo 1,4 elimination or ortho elimination due to closer proximity is known as ortho elimination. So this kind of skeleton is required. This is X and this is Y, and here I am writing A and this is B. Remember what is ortho elimination I am explaining? Is it aromatic molecule or not? Not only aromatic, even open chain is also possible, but most commonly applicable for aromatic. Is these two positions are ortho to each other or not? Now this is a radical cation. I am assuming that it is a radical cation. Now what happens, see, this is first position, second, third, and this is fourth. First carbon A I am removing. Fourth carbon B I am removing in the form of radical. And this bond I am breaking. So this radical, this radical, this radical, this radical forms. So can I put double bond here? Can I put double bond Y or not? Then what about here? So I can put double bond X, and this is radical cation. Then A and B will be removed out in the form of single bond. That is the answer. This is called ortho elimination. Ortho elimination is an example of 1,4 elimination. This point given in exam. In DL examination, in Telangana examinations, this point is given. Which among the following is a 1,4 elimination in mass spectrometry? Ortho elimination. Only this point is given in DL examination. Even set examination also, this question is important. Ortho elimination also called 1,4. If any aromatic molecule having a proper ortho substitutions is required. If there is no proper ortho substitution, this reaction is not possible. So there is a loss of atom from A, X, atom from Y, and these two will be removed in terms of neutral. See, this is neutral. And what is this? Radical cation. Is it a radical cation? Radical cation. Yes, this is possible. Aromatic molecules having proper ortho substitutions undergo 1,4 elimination or ortho elimination due to closer proximity. You may ask one more question, sir, why they are undergoing fragmentation? Reason is due to closer proximity. Closer proximity nothing but they are very closer to each other, ready to eliminate. So here A and B are very closer, that's why we are eliminating. Now generating molecular ion is very important in this case. Where you will generate molecular ion, that is a key point. Clear? So one example I will show, later you write down. See, this is a benzyl alcohol and here I am writing OH. So this is molecular ion. I want to do ortho elimination. See, this I am assuming as X and this is Y. Don't think that X definitely required radical cation. Don't think that X required definitely radical cation. Closer proximity with proper substitutions. So here what I am doing is I am doing heterolysis and here I am doing homolysis. Then what is the charge expected here? Positive. And here radical. And if I break this one homolytically, then radical cation or not? So can I put double bond here? Double bond. And below? Double bond O. Can I put radical cation? And what is removed here? Water is removed or not? See, what is the charge expected here? Positive. Positive and this one. Radical. Radical and radical. Double bond. Possible? So is it a one? See, whether I removed one group from 1, then whether I removed one atom from 4, this is 1. On 1, hydroxy I removed. On 4, I removed hydrogen. Is it 1,4? That point you need to focus. Don't remember blindly elimination. Where we are removing, that is a key point. So one example I will show, just give the answer. Here double bond, here this is OH, radical cation, and see, this is radical cation I am using. So can I remove water molecule? Here what is the fission? Heterolytic fission. And what about this hydrogen? Homolytic. And here also homolytic. Then what is your answer? So can I put double bond here? Double bond, and here double bond NH. This is radical cation. On first carbon I removed hydroxy, and fourth carbon what I removed? Hydrogen. So this fragmentation is possible. Okay. So even I can take a hydrocarbon over here. If these skeletons are appeared anywhere, you need to apply this. This is radical cation. Can you apply the same concept? Remove water molecule. See, remove hydroxy, this one, and this is homolytic. Then finally, double bond. Can I put double bond here? Double bond, and this is also double bond, and this is radical cation. Clear? Right. This is carboxylic acid, and this is OH. Here radical cation. Right, ortho elimination. So one example I will give, remaining you work out. Is it 1, 4? 1, 1, 2, 3, 4. On 1, remove hydroxy. On 4, remove hydrogen. Here also same. 1, 2, 3, 4. Here 1, 2, 3, 4. So here what should I remove? Hydroxy. And here hydrogen in the form of radical or not? And what about this bond? Radical. Same way. So here what you will expect? Here double bond. and this is carbon, and this carry C double bond O, and here double bond O. What is removed here? Water molecule is removed. And here what is the charge? Positive. Here radical. So can I write radical cation? Over. What is this dot indicates? Carbon. Will work out these three? Same, as it is same. So even esters also possible to show this reaction. This is C double bond OMe and this is hydroxy. Here hydrogen and here I am writing radical cation. So this is electrolytic fission, homolytic fission, homolytic fission. Will you get same answer or not? Here double bond oxygen, double bond O, and here double bond O. And what is removed here? There is a loss of methanol. This is MEO or not? MEO and this hydrogen is removed. Okay. Suppose if any amine group is present here, will you work out same? Here this is amine. This is C double bond O OMA. Give the answer. Same answer. And if any methyl group is present, will you get same? These all are asked questions in variable entrances. Means they given M by Z value, identify the skeleton. What is the proper fragmentation? What is this? All are 1, 4 eliminations. 1, 2, 3, 4. Here remove hydrogen, remove hydrogen, remove hydrogen. This carbon is assumed as 1, 2, 3. This oxygen is assumed as 4. This is X and this is Y. On X one group I am removing, on Y one group or atom I am removing. Finally the two are removed in terms of neutral. This becomes radical cation. So this is a most successful fragmentation. All are possible. So this I am writing as nitro, O minus, and this is plus, and here I am writing OH. See, nitro, and this is hydroxy, right? Now if I do 70 electron volts, apply 70 electron volts, it is also called electronic impact, both are same. Sometimes I will write 70 electron volts, sometimes electronic impact. Is it a molecular ion? Is it a molecular ion? Is it a molecular ion? Yes, this is not molecular ion. Now I want to generate molecular ion. So where should I remove electron? I want to remove electron from oxygen, which carry negative charge. Double bond O here. Negative means what? Extra electron or not. So I remove that electron, you will get like this. So this is lone pair, one radical. Then what is present here? Already hydroxy. So then next, now go for ortho elimination. In ortho elimination, this is 1, 2, 3, 4. Now this bond I am removing in the form of homolytic. This is homolytic. This is also homolytic. Homolytic. Now this is radical, and here radical, here radical, and here radical. Here also radical, here radical. So if you observe clearly, this is going to be removed in terms of, can I write double bond? Radical, nitrogen. This radical forms double bond, and this oxygen is as it is. And what is the charge on nitrogen? Positive. And here also double bond, right? And see how this hydrogen and oxygen is removed. Hydrogen is removed in terms of radical. This radical and this radical forms HO. Already lone pair. Here one more radical is there or not? Now what is this? Is it a cation? Cation. And what is this? Radical. And what is this? It is a radical cation. Radical cation. Radical cation undergo fragmentation to give cation and radical. Possible? Yes, it is possible. Depends on molecule, it may changes. Don't think every time we need to remove neutral. Follow rules. 3 rules I explained. Based on the 3 rules, we are writing the fragmentation. So not only aromatic compounds, even other than aromatic compounds also involve in ortho elimination. Otherwise you can say 1,4 elimination reaction. See, is it aromatic compound? No, it is not aromatic. It is not benzene first of all. But see, this double bond almost all looks like this double bond or not? This part is not there, but this double bond is as it is or not? Even these skeletons also involve in 1,4 elimination. But this is not ortho elimination. Why it is not ortho elimination? Why it is not ortho elimination? Because it is not aromatic first of all. You can say ortho, para, meta only when if it is aromatic. Clear? So it is an example of 1,4 elimination. It is 1,4 elimination. See, this is heterolysis. Then this is homolysis. And here homolysis. Then what is the charge? Positive, radical. So can I write like this? This is carbon and this is C double bond O. And here, this is carbon and this is CH2. And here, can I write radical cation? And what is removed here? Methanol is removed. That's it. It can also help in UV. In UV, I will ask this question. UV spectra. This is electrolysis. Here you will get positive. Here you will get radical. Radical, radical, radical. This positive radical I written as radical cation over here. These two. Here one electron and here positive charge. Now not two electrons. Right? That is ortho elimination and 1,4 elimination. So this is one more example for elimination reaction. Double hydrogen transfer. Double hydrogen transfer reaction is also a elimination reaction. Sometimes double hydrogen transfer also possible. Ortho elimination is over. Next is two hydrogens can also transfer. It is also one elimination reaction, but you need to focus on the molecule. Then only you can understand clearly. Okay. Now see this. What is double hydrogen transfer? And what kind of molecules can show this? Is it elimination reaction or not? Just you concentrate. Here double bond I am writing. This is C double bond O radical cation and this is oxygen. 1, 2, 3 and this is oxygen. Is it a molecular end? Yes, it is molecular end. See, observe clearly. Now here one hydrogen atom is present. Here also one hydrogen is there. Clear? Now I am breaking this bond. Homolytically I am breaking. And here also I am breaking homolytically. And here also I am breaking homolytically. How many center fragmentation? 3 center, right? So this oxygen carry radical. This hydrogen carry radical. This carbon radical, radical. And what about here? Radical, radical. Now the question is, see, when you break this bond, this bond, this bond in the form of radical, this hydrogen migrate from here to here. Try to understand. This hydrogen after breaking migrate from here to here. This hydrogen migrate from here to here. Clear? So then what is your answer? Now CH3O. Can you give the answer? This is C double bond O. Here. Lone pair. Next. Oxygen carry hydrogen or not? Here can I write positive? Positive or neutral? This is one electron. This electron forms bond. Then positive left as or not? Positive will be left on this oxygen. This oxygen radical take this hydrogen. So forms this one. Then what about this part? Is this oxygen carry radical? Here how many radicals are there in this carbon? On this carbon how many radicals? 2 radical. If this radical forms a bond, then how many radicals are left? 1 radical or not? So can I write like this? See, this is oxygen having initially 2 radicals, here 1 radical. This radical forming a new bond. If they form a new bond, you will get epoxy radical. Clear? Now observe clearly. Is it a cation? Now it is a cation. And what is this? Radical. Is it a radical cation? It is a radical cation or not? Yes. Radical cation undergo fragmentation to give radical and cation. Yes, it is possible. And important thing, see, on this oxygen any hydrogen is there? On this oxygen any hydrogen? No. On this oxygen any hydrogen? No. But finally see, it carry hydrogen and hydrogen. How many hydrogens are gained on this system? 2. That's why double hydrogen transfer. Is this reaction is right or wrong? Is it possible in mass spectrometry? If you leave this molecule in mass chamber, this fragmentation is possible. If anybody asks how it is possible means, you need to show evidence. What is evidence? Pathway, mass spectral pathway. Don't think that whatever direction it will take place. Never takes place. Suppose if you leave this pen over here, on which direction it will fall on surface? Any direction. Random. On which direction it may break? We don't know. Mass is not like that. It will follow one rule. According to the rule, it will break. What is the rule? 3 rules are there. First one, radical cation, radical cation, radical cation, radical cation and neutral. Even electron, even electron, even electron. If you know these 3 rules, no need to remember fragmentation modes. Any molecule if they given, you can confirm what is its empacid value, which fragment it is belongs to in 4 options. Is it clear? Let's take down. Here 2 hydrogens and here hydrogen, here radical cation. So break this, break this, break this. If I write dots, homolytic fission. Sometimes I will write like this, sometimes I will write dots. Same or not? As it is same. So what do you expect? Furon. This is furon and this is C double bond O. Hydrogen, positive, lone pair, oxygen carry hydrogen, right? This hydrogen migrates from here to here. This hydrogen migrates from here to here. Here how many radicals are generated? 2 radicals and here 1 radical. This and this combine together and you may get a 3-membered ring with methyl and this is radical. So whichever hydrogen is very close to this oxygen, it is going to be migrated. So don't think that every time it is third. That depends upon the ring size, depends upon the skeleton. Sometimes 4th hydrogen may be transferred here, sometimes 3rd hydrogen. Anything is possible. Clear? So that is double hydrogen transfer. So this is your last reaction or last fragmentation and last rule. It is also elimination. Skeletal rearrangement. It is the last fragmentation elimination and it is the last rule. In mass spectral rules, it is the last one. Almost all functional groups can show this kind of fragmentation. Skeletal rearrangement reaction. See, I am using oxygen. So this is R, and here see, this is radical cation I am using after electronic impact. Now I am breaking over here, I am breaking here one more. Then what will you expect? Here will get one radical or not? And what about this? Radical. Here one more radical or not? This radical forms double bond. And see, this R will come over here or not? This R comes from here to here. And this oxygen, this carbon carry double bond. So hydrogens are left over there, C double bond with H. So this is a radical cation and this is neutral. And this is radical cation. Yes, it is possible. We are eliminating formaldehyde or not? We are eliminating formaldehyde and one group migrate from within the molecule. This skeleton initially attaches to oxygen, now it is attaches to other oxygen. This is called skeletal rearrangement. Okay, one more I will show. They never go outside, it will migrate within the part of the molecule. Suppose if I take carbon having 3 fluorines, here fluorine and here fluorine. Suppose if I make electronic impact, you will get radical cation over here. Right? Here 3 lone pair, here also 3 lone pair. One electron if I remove, you will get 2 lone pairs and one radical cation. Right? Now, what I am doing is, here I am making homolytic fission. Here also making homolytic fission. Then what happens? This carbon carry how many radicals? 2 radicals. This carbon carry 1 radical, here 1 radical is there. This radical with fluorine comes and attaches here. Fluorine is attaches over here now. Now fluorine carry radical cation or not? This radical cation as it is. This radical attaches here. Now this carbon is removed in terms of, how carbon is removed? In the form of carbene. Is it a radical cation? Yes. Is it a radical cation? Is it a neutral? Carbene is a neutral. So this is called skeleton rearrangement. Always it will follow rule. Rule remains same. Clear? Right. So that is end of rules of mass spectral fragmentation. Clear? So can you revise that all rules? First, mass spectral pathways. 3 types of mass spectral pathways are there. 2 for odd electron, 1 for even electron. The three I explained. Later on, based on that pathways, we are applying how many possible fragmentations are expected, where we will cleave on a selective functional group. Starting from what we started? Mass spectral fragmentation rules. First we learn for alkane. What is the characteristic fission for alkane? Straight chain, loss of successive CH2, alpha heterolysis. Branched chain. What about branched chain? Loss of branched carbon having a maximum number of carbons in the form of radical. So alkanes can be identified by get difference by 14 units between two adjacent peaks. First peak is differ by 15, remaining all are 14. Later on we learn about cycloalkane. Loss of ethene is a characteristic fragmentation. Cycloalkane. Okay, then alkyl cycloalkane. Loss of alkyl in the form of radical. Then alkene, beta homolysis. Then alkyne, beta homolysis, retro-Diels order reaction. Okay, multi-center fragmentation. Later on what we discussed? Any halogen or oxygen, nitrogen or any heteroatom is present, alpha heterolysis, beta homolysis is a characteristic fragmentation. Okay, then we learn about haloarenes. If any halogen attaches to benzene, alpha heterolysis is common fragmentation. If any benzyl group is present, beta homolysis is a characteristic fragmentation. Then you will expect 91, 65, 39, 77, 51 common peaks for benzene. Later on we learn McLaughlin fragmentation or McLaughlin rearrangement. What is McLaughlin? Gamma hydrogen transfer followed by beta homolysis on unsaturated functional group. That will give olefin and enol. So any molecule having unsaturation bearing with a gamma hydrogen, they will undergo McLaughlin rearrangement. That McLaughlin rearrangement also is an example of Norris 2. Clear? Then we learn double McLaughlin. So what is double McLaughlin? Any unsaturated molecule, if 2 times McLaughlin rearrangement takes place, that is called double McLaughlin. As compared to McLaughlin, for CSR point of view, double McLaughlin is very, very important. How many, which among the following molecule undergo double McLaughlin, or which will not involve in McLaughlin? This kind of questions are framing very easily. Then indirect McLaughlin, then we learn ammonium ion fragmentation, finally carbonyl cleavage. After carbonyl cleavage, then we learn straightforwardly fragmentation, elimination. So fragmentation, elimination, dehydrohalogenation, dehydration, decarbonylation, orthoelimination, then double hydrogen transfer, finally skeletal rearrangement. So these are the total rules related to mass spectrometry. If you know these rules and pathways, you can apply this all on a individual functional group. So right now we are familiar to make fragmentation clearly. So if you know the rules and if you know the pathways, then mass spectrometry is almost all over. So now these all rules we are going to apply on individual functional groups. Means we are starting from alkane onwards. So we are going to learn what is the mass spectral fragmentation of alkane. So in your next class you will see what are the mass spectral fragmentations of individual functional groups starting from alkane. If I say alkane, you need to say what kind of fragmentations are possible. Okay, if I say alkene, what kind of fragmentation, what all possibilities are expected. Suppose if I say alkene, beta homolysis possible. Okay, then followed by unsaturation is there. So we can also expect a McLaughlin rearrangement. Triple bond also, beta homolysis, McLaughlin rearrangement. If any halogen is there, haloalkanes, alpha heterolysis, beta homolysis, okay, then followed by indirect McLaughlin possible, cyclation possible, like that. Means if I say any functional group, you are in a position to say what kind of fragmentations are possible. That we are going to learn in next class. This if you know only when rules are cleared. If you know rules clearly, pathways clearly, then only we can operate these all rules and individual pathway and functional group. So that spectra of corresponding molecule will be clear for you. Okay, so that we will discuss in your next class. You try to prepare up to these rules and pathways only. Okay, so these rules and pathways will not be discussed one more time because tomorrow I am planning to start a new chapter. GOC I am planning to start, General Organic Chemistry, because tomorrow we are announced a new batch. So for new batch students, if I explain from here, they won't understood anything. So for that, what I am saying is, tomorrow I will explain completely GOC, General Organic Chemistry, a new chapter, so that your maximum basics will be cleared in that particular concept. And this will be explained parallelly after 1 week. After 1 week, 2 concepts will be going on. First one is GOC. Parallelly, if my class will be there up to 8:30, first hour I will take GOC, next hour I will take mass spectrometry. So this 1 week, your work is try to rewind the all mass spectrometry recording video classes. Especially we are uploaded in YouTube. Try to listen that all level videos up to today class. Total level videos are there. So within this 1 week, try to work out that all videos so that whenever if I start 12th class, this all rules I am going to dump on individual functional group. On that time it is not easy to understand. Those who are new for this class, those who are new for last 4 classes, little bit better. 4 classes you can scope up. But those who are new for this class, if I apply on any individual functional group, it is impossible to understand. So I am giving some time, hardly 1 week I am giving. Okay, so within this 1 week you try to rewind the all mass spectrometry classes. They are available free in recording video, especially in YouTube. That won't be stay permanently in YouTube. Only for few days we are uploaded in YouTube. Okay, so try to work out as well as possible. Later on that all videos will be available in your app. That will be there for 1 year. So your work is try to work out all mass spectrometry videos as early as possible. Because these rules I will ask, pathways I will ask during start of your next mass spectrometry class. 1 day before I will announce when I am going to take mass spectrometry class. On that day try to prepare and come. Okay, so we'll stop here, we'll continue next class. So tomorrow timings remain same, 5:15 to 7. Okay, so new class, if any choice is there, we are going to extend either half an hour or 40 minutes. That depends upon availability of faculty, but most probably you have only one class. After 23rd onwards, around, so because 23, 24, some holidays are coming right now. So that's why I'm saying. So tomorrow maybe you have 1 class or 2 class, that is not confirmed yet, but 1 class is compulsory. Maybe time may be extended up to 7 or 7:30. Suppose if only 1 class is there, that will be there up to 7 o'clock. If 2 classes are there, that will be there up to 7:30. Okay, mostly you have only 1 class only. If any introduction part is there, that will be introduced in your class directly by other faculty. Clear? We'll stop here.